Okay, so now what are we going to do with this AMU thing? Because we talked about that before. We talked about how a proton weighs 1 AMU, a neutron weighs 1 AMU, and that corresponds to the mass number of the isotopes. But it doesn't match. The mass number doesn't match those numbers on your periodic table, but they're close. And the reason why they don't match is because in nature, in the real world, most elements occur as a mixture of 1 or 2 isotopes. And remember, definition of isotope is they have the same number of protons but different numbers of neutrons. Therefore, their mass is different. And so atomic mass, which is what is actually on your periodic table, is an average. And it's based on each isotope has its fixed mass, protons and neutrons, and how much exists in the real world. Okay? It is measured in atomic mass units, which is the same thing as the mass number, but the average atomic mass is based on its percent abundance as well. It's a weighted average, not a mathematical average. You don't add up and divide by 2 or 3 or whatever. So for example, all in the real world, there are 2 naturally occurring isotopes of chlorine. Both of them have 17 protons. This one has 18 neutrons, and this one has 20 neutrons. Therefore, they weigh different amounts because the majority of the mass is in the protons and neutrons. Of all the chlorine in the world, about 75% of it weighs 35, and only 25% of it weighs 37. So the average atomic mass of chlorine, the element chlorine, is going to be closer to 35 than 37 because more of the chlorine in the world weighs 35. Okay, it's a weighted average, and if you look it up, it's 35.453 AMUs on the periodic table. So, the way you find average atomic mass, the number, this is the number on the periodic table, the decimal number. Okay, it is a weighted average of the mass of the atoms in a naturally occurring sample of the element. It accounts for both the mass and the percent abundance of the isotopes that are present. The equation is a little weird, okay, but in order to do it, you need how many isotopes there are, how much each one weighs. Remember, it's the mass number, protons plus neutrons, and how much of it there is in the real world, and I will give you that. And the way you calculate the average atomic mass, this would be the number on the periodic table, you take the percentage of the first isotope, divided by 100. So we want it as a decimal percentage, multiplied by how much that one weighs. Add it to the percentage of the second one, divided by 100, again, a decimal number, times the mass of its isotope, and the last one. And if you had more, you would do more. If you only had 2, you would stop. But you just keep going and going and going for however many elements there are. So, for example, carbon has 2 stable isotopes in the real world. Carbon-12 has an abundance of this. Carbon-13 has an abundance of that. Calculate the average atomic mass. So average atomic mass equals the percentage of the first isotope, 98.89 over 100, times how much it weighs, which is 12, added to 1.11 over 100, times how much it weighs, which is 13. Now, if you have a graphing calculator, you can just do this straight away on your calculator without any parentheses. So 98.89 divided by 100 times 12. Literally, just type it in. Then hit the plus sign. 1.11 divided by 100 times 13. And your calculator will spit out an answer at you of 12.0111 AMUs is the unit. In terms of sig figs, we're not going to worry about sig figs. It's too complicated. Okay, this is an absolute number, this is an absolute number, and then it's complicated. So we're not going to worry about it. You want to call it 2 decimal places, we'll call that good. All right, so go ahead, take a minute, pause the movie, see if you can do this one. Okay, calculate the average atomic mass of bromine. So AAM equals, go ahead, set up the equation. Now if you notice, they're almost 50-50 split. That means your average mass is going to be 50% in between each of those. It's probably going to be right around 80. So let's go ahead and set it up. Sorry. 50.69 over 100 times 79 Add it to the next one, 49.31 over 100 times 81. Type it in. If you have a graphing calculator, you can just type it straight in without having to do anything other than type it in. Add it directly to 49.31 divided by 100 times 81. And I got 79.986. And I think there's a 3. Nope, that's a 2. AMUs. And again, if you wanted to call it 79.99 AMUs, that would be totally fine by me. Okay, so it's a pretty simple equation. The big thing to remember is put them over 100, and if you have a graphing calculator, type it straight in. Go ahead and see if you can do this one. Okay, so it's an unknown element. It's not on the periodic table. That's one of the things. You can kind of check your answer on the periodic table. So the average atomic mass equals 13.5 over 100 times 288 plus 3.5 over 100 times 289, then I'm missing a percentage, right? I don't have a percentage here. Well, don't forget, the way percentages work is they will always add to 100. So if I take 100 minus 13.5 and minus 3.5, what I get is 83. So I'll put 83 over 100 times how much it weighs, 291. Okay. I'm going to pause the movie, and you can just literally type it in on your calculator if you have a graphing calculator. And so what you get for an answer is 290.525 AMUs. Don't forget units. If you wanted to call it 290.53, that would be fine. Okay. In terms of understanding what it means, well, if you look at the percentages, this one was 83%. 83% of all this element weighs 291, which is why this number is closest to that value. Okay. It's way far away from 288 and even 289. It's much closer to this one because the majority of the element exists as that isotope. Okay. Go ahead and see if you can find this one. This one's a little bit different math. I would expect you guys to be able to do it. So first of all, let's find that missing percentage. 100 minus 78.9 minus 10 is 11.1%. Sorry, 11.01%. Okay, but now we're looking for the missing mass. Okay, this requires a little bit of algebra, and I'm going to switch over to the other side to do it. I think I have a blank slide. Yep. So the average atomic mass equals the first one, 78.99 over 100, times how much it weighs, which was 24, plus 10 over 100, times how much it weighed, which was 25, plus the 11.01, which we found, times how much it weighs, which we don't know, and I'm going to call that x. Okay, and this number was given in the problem. It was 24.305. It came right off the periodic table. Okay, that's magnesium. Equals these numbers. I'm going to multiply these two. This is an example where you do not want to do it all on your calculator at one time. And so I get 18.9. And I'm just going to keep all my sig figs for right now, just because I want to make it a little simpler. 2.5. And then here, so this is the 2.5. This, when I multiply it, is 0.1101 times x. Now, these are not like terms. You cannot combine the 18, the 2.5, and then the variable. You can combine this. And you get 21.4576 plus 0.1101x. And again, you still can't combine the number and the variable. However, you can subtract this from both sides. So it requires a little bit of algebra. not outside your reach. I think you guys can certainly do this. That goes away. You get 0.1101x equals 2.8474. And now you can divide. And x ends up being 25.86. But since we're looking for one of these numbers, we're going to round that to a whole number and call it 26, and then the units would be AMUs. Okay? So you would expect to get a number that's pretty close to, you know, these guys, 24, 25, 26. Doesn't mean it's necessarily a numerical order. But if you got a number like 40 or something, or certainly a negative number, that's way off. Okay? So those kinds of problems I absolutely think are within your reach. This one's a little bit harder. Okay, this one is an extra credit level problem. This is something that I would typically assign to my AP Chemistry students as a requirement. However, if you are not going to plan on taking AP Chemistry, or you don't want to really push yourself so much, then I would just stop the movie right now. Okay, I'm going to show you how to solve this. If you're curious, it's not that hard. You've got two naturally occurring isotopes. And the average atomic mass of chlorine came right off the periodic table. So I'm going to do this over here. 35.453, that's the average atomic mass, equals the percentage of the first one multiplied by 35, added to the percentage of the second one multiplied by 37. The thing is, you don't know either percentage. I mean, one of them might be 40, and one might be 60, one might be 10, and one might be 90. But you don't know what either one of them is. What you do know is that they add up to 100. So whatever this is going to be 100 minus that, because they add to 100. Put this over 100, put this one over 100, and you should be able to go. Remember, you have to turn those percentages into decimals. Now, algebraically, this is not a whole lot of fun. There's an easier way of solving it. And if you're pretty good with math, maybe you'll follow along when I say what I'm doing. Still setting it up the same way. The thing is, I'm not going to take those percentages and turn them into decimals. I'm going to say x is a decimal. And x is a decimal might be 0.1, in which case the other one would be 0.9. Or it might be 0.4, in which case the other one would be 0.6. So the mathematics of it is that if this is considered, if I can recognize in my head that I'm keeping this as a percent, as a decimal already, then this one is 1 minus that value. Not 100, 1, because all percents as decimals add to 1. So now it makes the math a little easier. 35.453 equals 35x plus 37 minus 37x. Don't forget to distribute. Okay, combine like terms. My variables are my like terms. So I have 37 minus 2x equals 35.453. I'm going to subtract the 37 now. So 35.453 minus 37 is a negative number, but I'm not done with the algebra yet, so I'm not going to panic over a negative number yet. Equals negative 2x divided by negative 2. You get 0.7735. So what that's referring to is this value right here, 77.35% weighs this much. If I subtract that from 1, I get 22.65% weighs this much. So it's not that hard. It does require a little bit of algebra, a little bit of thinking. This trick makes it a lot easier than doing it this way. Because people screw up the algebra. But if you want to do it this way and you're careful, you should be fine. It's no problem at all. Just you got to kind of make sure what you're doing. Okay? And I'll give you guys time to practice it in class.